Hello all. In this video I'm going to go through each of the proofs of the circle theorems that you need for GCSE. I'm doing this using the Maths Genie proofs of the circle theorems exam questions. You could do this using any circle that you wanted, but I just thought this was easier and that I could show you on the circles how to do these proofs. Okay, so the first one is A, B and C are points on the circumference you can see on the circle. Prove that angle AOC is twice the size of angle ABC. You must not use any circle theorems in your proof. So basically, I'm proving that the angle at the centre is twice the angle at the circumference when they are subtended by this same arc down here. So, let's do this. First of all, I'm going to split this sort of internal shape here down the middle. Now, I can't necessarily assume that I've split this perfectly in half because this point here is not unique. It could be anywhere on the circle. So what I'm going to do, I'm just going to label these two angles X and Y. Now, because the line I've drawn here is a radius, goes from the centre to the edge of the circle, and these two lines here are radii, that means I have two isosceles triangles here, which means that just here I have an angle of Y, and just here I have an angle of X. So let's have a think now about these two internal angles. Well, angles in a triangle add up to 180. So this one here is going to be 180, take away X, take away X. Or 180, subtract 2X. This angle in here is going to be 180, subtract 2Y for the same reason. Now, to get the angle in the middle that we want, angle at the centre, we need to do 360 subtract these two angles that I've just worked out, because angles in a full turn add up to 360. So we're doing 360 subtract 180 subtract 2y subtract 180 subtract 2x. Well, that's 360 subtract 180 add 2y, because a negative times a negative makes a positive, subtract 180 again, and then add 2x for the same reason. Well, 360 subtract 180 subtract 180 makes 0, so all I'm left with is 2x add 2y, and if I factor out 2, I find that this is actually double x plus y, and x plus y is my angle at the circumference. So I've just proved that the angle at the centre is half the angle at the circumference. Sorry, the angle at the centre is double the angle at the circumference when they're subtended by the same arc. Okay, let's keep going. A, B and C are points on the circumference of a circle, centre O. AOC is a diameter of the circle. Prove that angle ABC is 90 degrees. You must not use any circle theorems in your proof. Now, if this line wasn't here, this would be a really short question, because all we have to do is invoke the previous circle theorem, angle at the centre is twice the angle at the circumference. This is an angle of 180, which must make this an angle of 90. However, if we want to prove it without circle theorems, we would do the following. Okay, so first thing we're going to do, we're going to go from the centre and then just split my semicircle triangle into two different triangles here. And once again, because we are working with radii, we are going to have two isosceles triangles. So let's put some labels on. we have x here and y here. Well, that means I have x here and y here also, because of an isosceles triangle. So these two angles in the middle we can work out again. You notice there's some similarity here with the previous proof. So this angle in here is going to be 180, take away x, so that's subtract 2x. And this angle in here is going to be 180, subtract 2y. But because these two angles are sitting together on the diameter of the circle, and you can check the question, AOC is a diameter, that means they must add up to 180. So we have 180, subtract 2x, add 180, subtract 2y is equal to 180. Well, I can subtract 180 from both sides, and that gives me 180, subtract 2x, subtract 2y is equal to 0. If I then add 2x and 2y to both sides, I get 2x plus 2y equals 180. And because I have a common factor of 2 on every term in this equality, I can do x add y equals 90. Or x add y is my angle here. So that means my angle at the circumference, angle ABC in this case, is 90 degrees, or a right angle. Okay, right. Let's continue with this question. So, this question says, A, B, C and D are points on the circumference of the circle, centre O. Prove that angle ABD and angle ACD are equal. Basically here, we're proving that angles in the same segment are equal. Now, what we can do to do this is we can just draw two straight lines from the points on our segment to the centre of the circle. Then we have that angle ABD is equal to, so angle ABD is equal to, if I call that x, 1/2 x as angle at the centre is twice the angle at the circumference. So again, using that first theorem that we proved, circumference, there we go. However, I could also say the same thing about this angle here. So I've applied the angle at the centre is twice the angle at the circumference argument for this angle, but I could also do the same for these two angles. So all I need to do is write angle ACD is equal to 1/2 x. For the same reason, in the exam, I would write exactly the same thing. Again, I'm not doing that here just because it's a bit of a waste of time. So that means that angle ABD equals angle ACD equals 1/2 x. So those two angles are the same. Okay, let's keep going. A, B, C and D are points on the circumference of a circle, centre O. Prove that ABC and ADC add to 180 degrees. Again, this time is basically a rewording of the cyclic quadrilateral theorem, that opposite angles in a cyclic quadrilateral sum to 180 degrees. So again, what we're going to do is we're going to draw two lines on here just to make life easier. So one from A to the centre and another one from O to the centre. Now, what I can do, I'm going to label this angle X and this major angle Y. Well, ADC, angle ADC, is equal to 1/2 X, because angles at the centre are twice angles at the circumference. I'm just going to copy that argument from up here. Save me rewriting it all. Here we go. Then I can also say that angle ABC is 1/2 Y for the same reason. So angle ABC is 1/2 Y for the same reason. Again, in the exam, I would write the reason. I'm just not here because it's not necessarily required. However, X add Y has to be 360. Well, that's because angles in a full turn equals sum to 360 degrees. So, if I add together this 1/2 X and 1/2 Y, my angle ADC and angle ABC, add angle ABC, is that definitely the right letters? Yep. That is equal to 1/2 X, add 1/2 Y, which is equal to 1/2 X plus Y. Well, X plus Y, I've just said, is equal to 360. So that is 1/2 times 360, or 180. So cyclic quadrilateral, the opposite angles in this cyclic quadrilateral, in this case these two angles, add up to 180. If we were asked to prove it for the other two angles, the angle at C and the angle at A, we would just draw our lines here and here instead. So the exact same proof works for the other pair of opposite angles. You just need to reposition the lines you draw ever so slightly. Okay. A, B and C are points on the circumference of a circle, centre O. DCE is a tangent to the circle. Prove that angle BCE and angle BAC are equal. So let's identify these angles. BCE and angle BAC. So here we're essentially being asked to prove the alternate segment theorem. And to do so, what I'm going to do is I'm going to draw a diameter here. So I've got a diameter going from the very bottom of the circle where my tangent meets through the centre all the way to the other side. Then from that diameter, I'm just going to draw an extra line here that meets at B so that we have two angles in that same segment. Just adjust the position of that slightly. There we go. So if I can prove that this angle is equal to this angle, well then I've done it, because angles in the same segment are equal. We proved that earlier. So let's do this. First of all, I'm going to call BCE X, and then we're going to work from there. Well, we know that angle OCE is 90 degrees because tangents meet radii, or diameters, at right angles. So that means that angle just here, OCB, is going to be equal to, just draw a little arrow here, that is going to be equal to 90 subtract X. Well, what I also have just here, just highlight it for you, must be a right angle, because, if I zoom in a bit, this is the same setup as my angle in a semicircle proof from earlier. If I'll just scroll back up to that. here, I proved that the angle in a semicircle, i.e. the angle from the two ends of a diameter to a point on the circumference of the circle, has to be 90 degrees. So, if I go back down, that tells me that this angle just here is 90. So, using angles in a triangle, I can say that this angle just here is 180, subtract 90, that's subtracting this angle here, and then I need to subtract my other angle, which is 90 minus x. So let's do that. 180 minus 90 minus 90 minus x, close bracket. Well, 180 take 90 is 90. And then if I bring that -1 into that bracket, that's subtract 90, add x, because a negative times a negative makes a positive. 90 take 90 is 0, so that angle must be equal to x. So that means that this angle here, the angle I'm aiming for, must also be equal to x. So angle BAC, angle BAC equals x, as angles in the same segment are equal. So that is how you prove the alternate segment theorem. Right, that is everything we've covered for today. So just to summarise, we proved that the angle at the centre is twice the angle at the circumference. We proved, without using the angle at the centre theorem, that the angle at the circumference of a semicircle has to be a right angle. We proved that angles in the same segment are equal. That came in useful later as well. We proved that opposite angles in a cyclic quadrilateral have to add up to 180. And finally, we proved that the alternate segment theorem is true. That's by using a combination of things, including that there's a right angle in a semicircle, that tangents meet radii at right angles, and using that angles in the same segment are equal. Hopefully this was helpful. Let me know if there are any other topics you want me to cover.